We have day and night due to the orbit of Earth around the Sun, coupled with Earth's rotation on its axis. This natural phenomenon originates from the structure and motion of our planet. Here's how we have day and night. Orbit around the Sun. Earth moves around the Sun in an elliptical orbit. The Sun is located at one of the two focal points of this ellipse, referred to as one of the 2 points of day and night. Rotation on its axis. Earth rotates on its own axis, known as the rotation axis. The time it takes for Earth to complete one full rotation on its axis is called a day. Impact of sunlight. As Earth rotates on its axis, a portion of the planet receives light from the Sun, creating daytime in that region. Simultaneously, another part of Earth is in the shadow, not receiving sunlight, resulting in nighttime. Seasonal changes. Throughout the course of a year, Earth not only rotates on its own axis but also orbits around the Sun. This introduces variations in the angle of sunlight on Earth's surface, causing changes in the length of day and night. In summer, a specific region may receive sunlight for a longer duration, resulting in longer days, while another region may experience shorter days. In summary, day and night occur due to the combination of Earth's orbit around the Sun and its rotation on its axis, coupled with changes in the angle of sunlight throughout the year. We have day and night due to the orbit of Earth around the Sun, coupled with Earth's rotation on its axis. This natural phenomenon originates from the structure and motion of our planet. Here's how we have day and night. Orbit around the Sun. Earth moves around the Sun in an elliptical orbit. The Sun is located at one of the two focal points of this ellipse, referred to as one of the 2 points of day and night. Rotation on its axis. Earth rotates on its own axis, known as the rotation axis. The time it takes for Earth to complete one full rotation on its axis is called a day. Impact of sunlight. As Earth rotates on its axis, a portion of the planet receives light from the Sun, creating daytime in that region. Simultaneously, another part of Earth is in the shadow, not receiving sunlight, resulting in nighttime. Seasonal changes. Throughout the course of a year, Earth not only rotates on its own axis but also orbits around the Sun. This introduces variations in the angle of sunlight on Earth's surface, causing changes in the length of day and night. In summer, a specific region may receive sunlight for a longer duration, resulting in longer days, while another region may experience shorter days. In summary, day and night occur due to the combination of Earth's orbit around the Sun and its rotation on its axis, coupled with changes in the angle of sunlight throughout the year. A black hole is a region in space where gravitational forces are extremely strong, to the extent that not even light can escape from it. The gravitational pull is so intense that it forms a boundary known as the event horizon, beyond which nothing, including light, can escape. Here is how black holes are formed and how they operate. Formation of black holes. Black holes typically form when a massive star exhausts its fuel and undergoes a gravitational collapse, creating a highly concentrated mass in space. The energy released during this collapse can generate an extremely strong gravitational pull, creating a black hole. Black holes can also form through the collapse of other celestial bodies or through the merging of smaller black holes. Acceptance of gravitational force. Black holes exert an incredibly strong gravitational force. For a non-rotating black hole, the event horizon is the boundary beyond which no object, including light, can escape the gravitational pull. Anything that crosses the event horizon is drawn into the black hole and cannot return. Rotation around an axis. Some black holes have the ability to rotate around an axis, creating a swirling effect and unique physical phenomena like spinning around a black hole. Hawking radiation. Stephen Hawking's theory predicts that black holes can emit a small amount of thermal radiation through a phenomenon known as Hawking radiation. This implies that over time, black holes may lose mass and energy through this process. Impact on surrounding space. Black holes can also warp the space around them, causing space-time to curve and even affecting time in an effect known as space-time curvature. Black holes are one of the most intriguing phenomena in physics and astronomy, serving as a deep area of study in both fields. If an object falls into a black hole and crosses the event horizon, according to modern theories of black holes, it cannot escape for the following reasons. Incredibly strong gravitational force. Black holes possess an extremely strong gravitational force to the point where space around them is profoundly disturbed. This results in a gravitational pull so strong that any object crossing the event horizon is drawn into the black hole. Event horizon. The event horizon is a virtual boundary around a black hole where the gravitational force becomes strong enough that even light cannot escape. If an object passes this boundary, it has fallen into the black hole and cannot return. Exceeding the speed of light. As an object approaches the event horizon, it needs to move at a speed greater than the speed of light to escape the gravitational pull of the black hole. However, according to the theory of relativity, this is not feasible. Speed beyond the speed of light. As an object delves deeper into a black hole, the gravitational force becomes increasingly stronger. The object will experience an infinite gravitational pull, implying that it will be compressed and stretched infinitely, losing its original form. These characteristics make it impossible for any object, including light, to escape the gravitational pull of a black hole after crossing the event horizon. This is a crucial aspect of modern black hole theory in physics. Space exploration has provided us with crucial knowledge and deep insights into the universe. Here are some key things we have learned from space exploration missions and endeavors. Understanding of the solar system. Space exploration missions like Voyager and Pioneer have provided valuable information about the planets and objects within the solar system, enhancing our understanding of their structures and characteristics. Features of planets and the Sun. Missions such as Cassini-Huygens have expanded our knowledge of planets within the solar system, such as Saturn and its moons, as well as the characteristics of the Sun. Understanding of cosmic chemistry. Knowledge of elements and compounds in the universe has been extended through research on planets, stars, and nebulae using devices like the Hubble Space Telescope. History of the universe. Missions like Hubble and the Kepler program have helped determine and measure the distances between stars and planets, aiding in constructing the history of the universe's development. Knowledge of exoplanets. Discovering hundreds of exoplanets through missions like Kepler has opened up opportunities to search for extraterrestrial life and understand the diversity of planetary systems. Study of black holes and neutron stars. Missions like LIGO and Virgo have detected gravitational waves from events such as black hole collisions and neutron star mergers, providing crucial information about the structure and properties of these objects. Assessment of universe formation and evolution. Observing stars, nebulae, and star clusters contributes to accumulating knowledge about the formation and evolution of the universe from its earliest stages to the present. These findings not only enrich our knowledge of the universe but also contribute to a profound understanding of the nature and origin of life on Earth and within the cosmos.